questions. Okay. So I forgot to have one of you flip, so I'll just flip. So hey, Muggles, come on down. And what is one helpful tidbit on your model summary board that's going to help everybody turn things around and get things headed in a better direction on the test tomorrow?
Conservation of momentum is important. So,
how's that work?
Colliding objects both experience the same amount of momentum, which is in units of kilograms times meters over seconds. So therefore, heavier object, like in a collision, the heavier object will come out of it with a lower magnitude of velocity than the lighter object.
Always?
I can't think.
Okay.
Well, unless they stick together.
Okay. Then they would have the same amount. Okay. What's going on? Do you have an if chart there, or what is that? No.
We kind of ran out of space because
Okay.
we wrote too big, but you would use if charts to figure out, like, equalize the momentum, so you could figure out the velocity or mass of the objects.
What do you mean when you say equalize the momentum?
So when two objects collide, they end up, after the collision, they have the same momentum. So you would use an if
Same
chart.
momentum as each other?
Yes.
Those don't have the same momentum as each other.
Well, this is like before a collision. This would be like the initial, like we ran out of space.
These are just examples.
Yeah, these are just examples of graphs you could use. So this one would be like an initial, and then if we wanted a final, it would look something like that. Right?
So
I'm not doing a good job.
still kind of fishing for what is the thing that's the same.
The
before and after.
area of this right here. So 10 kilograms times 5 meters per second, 50 kilograms times meters.
It's like after
So
they
you're
collide.
saying
Then
that-
the air after they collide, these two areas would add up to
There we go. That's what I was fishing
Yeah.
for. So whatever the initial total momentum is, you're going to have the same final total momentum.
yeah. And
Okay,
this,
I can get with that.
yeah, this is a bad representation because like one of them should be going in the other direction. So I'll just erase it.
All right, go ahead and flip another board for us, please.
I don't know.
Go for it.
No.
All right.
Uh-oh.
All right, Slytherin. So,
I don't know which thing to do.
in these problems of conservation momentum, the total initial momentum is the same as the final total momentum. What are some other important things to know?
For instance, if you increase the amount of time during the collision, then the force is less applied, and then if the force is increased, then time will be decreased.
To have the same change in momentum.
Okay. So, the same change in momentum can result from different combinations of force and time. Smaller forces require bigger times. Smaller times require bigger forces to have the same change in momentum.
Yeah.
Okay. Thanks, Slytherin. Go ahead and flip another board there for us. All right. The group called 80. Oh, okay. That'd be cool. That should be a grouping theme sometime with 80s girls' names. All right. Dibs on Jennifer. All right. What do you got here for us?
There's two types of collision, inelastic and elastic.
Ooh, what's that mean?
In an inelastic collision, the two objects are not bouncy, so they're sticky. And so after the collision, their velocity changes.
Yeah, they stick together, right? Okay, so that'd be inelastic. If they're bouncy, what happens?
If they're bouncy, then they like bounce off of each other. And so
That's what it says.
the two objects, they experience the same magnitude of force, but they're in different directions.
Alright, thanks Amy. Go ahead and flip another board. Alright, so same initial and final momentum. Same change of momentum can result from different combinations of force and time. Sticky, bouncy. What else do we need to know about?
Impulse is
Okay.
the change of momentum.
Ooh, the most important word in the sentence that you just said was change, okay? There's a triangle in front of the P, okay? That means that we're talking about the change in momentum is equal to the impulse. So like, that seems simple enough, right? But that's gonna be the reason that most folks are in tears after tomorrow's test, just letting you know, okay? Goes to physics yet to come. So be aware of that. Impulse relates to the change in momentum. That's different from the final momentum. All right, Chris, go ahead and flip another board for us. Here comes Durmstrang. All right, Durmstrang, what else is important to know?
Yeah, kilograms times meters per second.
Is equivalent to. Okay, that's important to know. All right, not to pick on these lads, but there's a good teachable moment up here. What about their if charts is impossible? Run that by your neighbor quick. Don't do that. Mistakes are mandatory, Quacky. All right, what's Quacky need to do to right that wrong? Correct. We're not studying that yet. Give it a day. He's a soccer player. Don't expect him to take things down out of the air. All right, Quacky, why did you have to do that? Yeah, there you go. Couldn't happen that you had only positive initially and then ended up with negative in the end. All right, cool. Thanks, Durmstrang. Go ahead and flip another board. All right, Ravenclaw. What do you got for us?
I don't think anyone's done the force v time graph.
Instead of just thinking it, can you say it out loud?
So this is like a graph of the impulse. It has like force on the y-axis and time on the x-axis, and like the area underneath like the force line, force curve is the impulse because it's Newton's times seconds. Thank you. And that's equal to like the change in momentum, like this area minus this area.
Change in momentum, right? Two groups have told you. Yeah, you're still going to be tricky. Wow. All right, go ahead and flip another board. I think there's one hiding up there. Yeah, secret board.
We didn't hide it, we got hit.
Yeah, that's what they all say. Who got caught? This group is called collisions. What are you?
We're another, wait a second now.
You are.
Another Amy.
No, you're not.
We are.
Yeah, they are.
There's two armies? No, there's not.
Yes, there is.
That's a mistake. Ah, crap. How did that happen? What got screwed up here? All right, give me a second.
You can just.
No, I don't want
You
this.
have to put it in one Amy.
No class can have two Amy's. All right, I need Hufflepuff, I need Gryffindor. Do I have a Ravenclaw?
Yeah.
Durmstrang,
Yes.
Slytherin.
Yes.
Is there a Slytherin?
Yes.
Okay. Dumbledore's Army, yes, clearly. Muggles.
Yes.
All right, you're gonna be. Do we not have that?
We have mine.
Yeah, you're the Death Eaters. All right, cool. You're the Death Eaters. All right, Death Eaters, what's up? Eat some death.
Momentum.
What about it?
It's conserved before and after a collision.
So that's kind of crucial. Like, you don't have an if chart, but a lot of people have those up there. So, like, you look at those if charts. Like, look at this one on the end here with Ravenclaw. What happens in between the initial and the final? I'm going to throw that question to everybody, but these two up front are going to huddle and talk about it, and then we'll come back to them. But what happens between the initial and the final? Okay, this is kind of important, because when you're reading a problem, you have to know when in time is I and when in time is F. So what happens between initial and final?
And they're going in the same direction. So they must have.
I'm asking you now.
Well, it looks like there is spontaneous collision because velocities are the same.
Okay. So you can kind of not read from that one, but I guess what I'm looking for is more generally what happens between initial and final.
The second object gains velocity. Instead of going in the negative direction, it starts moving in the positive direction, and then the other one moves more slowly in the positive direction.
Okay. So that's still like kind of like specific to a situation. I'm thinking generally. Does anybody get a word out there for me? What happens between initial and final? Okay. Koba, can you say that louder? They're touching, which is not fancy for their whatting. Interacting, okay, right? They're touching each other, they're interacting with each other. So be mindful of that when you're trying to place like the if chart and think about when in time is this happening. You want to identify when is the interaction between these objects, and the I happens before they're interacting with each other, and the F happens after they're interacting with each other. That's kind of subtle, but that's really important for a while. All right, go ahead and put the last board for us. Again, Kyle, that's the next unit. No spoilers. All right, here comes Hooplepoop. 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 What else you got for us?
Good question. What do we got? We have different colors. We have that equation. I don't think we said that yet. It's when you put on the board yesterday, like the weird third child we were talking about.
Yeah.
That helped me out in one of the math strings, like the third question of part 2 or something.
Sure. Anything else that was helpful on mastering?
Coming at it again later.
Fair enough. All right. When we look at your if chart, what should we know about what's happening there?
Whether it's well, hang on. First, we have the elastic one and the inelastic one, where
How can we tell them apart by looking at them?
because in inelastic one, they stick together after they have the exact same velocity after.
Okay.
Okay. In elastic one, they're bouncing away from each other. They're not sticking together. They don't end up at the same velocity necessarily.
Fair enough. All right. Cheers. All right. I took some pictures of earlier boards in the day, so I'll post those on the canvas here. Which is to say, I'll forget to post them on the canvas here. If you want to take pictures of those boards real quick, that's cool. But then we're going to erase those and head on over to Care Deck for a little bit of review. So join us in the session. Yeah, or phone. Yeah, phone. But you, well, yeah, I need my phone. You can use your phone. I need to have the 3 screens. All right, the join code is BBMJQ. And then go ahead and clean your boards. Stick to golf.
Wait, I liked your board.
Oh, okay, you did.
Just trying to get a photo.
Do you want her pose with the board?
No, get the.
No, that
Get
board
the
too.
dog
No,
bears.
stop, no,
Bears.
picture. Stop her right there.
The coma.
If you'd like to pose with the board. you're
No,
welcome.
I don't want to post.
Whoa, picture.
Jonah, if you could stop interacting with Kyle, that'd be cool.
Technically, he was interacting with me too.
Of
course, there's words. The interaction with Jonah. How do you know? That's nice.
All right, BDMJQ, and the first question is this: what's this card's change momentum? It's no one's surprised it's Durham strain that needs to come clean their board. Join code again, BDMJQ. What are those from?
There you go.
Clearly we have multiple. Did some stupid college hand those out or something?
Dumbass.
Mr. Audia.
This is why I don't.
How
know
many
story.
people can Alex hit with things in class today?
I didn't hit him when I threw the marker up.
Fair enough, but it was
I did not hit you,
pretty
correct?
close. Had a little whip on it. That's okay. All right. Much like an STI, could you please keep those to yourselves? Thrilled that that's in the audio recording of this class. So, all right, I've got 10 of you in. BDMJQ. All right, and nobody's voting for C, but somebody's voting for everything else. So talk to your neighbor real quick about what you got and why.
If you look at this, this is like 20 kilograms.
Well, if it's gonna be the negative part.
Negative 20 is
All right, we got 13 for E and 2 for B. So why E, one of you 13?
I see.
Do you guys want to waste Ronan on this one? Go for it, Ronan.
I think it's E because it starts out traveling in a negative direction. And if you get its momentum, that's mass times velocity, you get 10 times 20, or 10 times 2, that's 20 Newton seconds. And the second picture is moving the opposite direction, so positive 1 meter per second times the same 10 kilograms of 10 meters, or 10 Newton seconds. And the difference between negative 20 and 10 is positive 30.
Be mindful of that if you haven't done the tennis ball problem on the mastering yet. Okay, like this is the tricky thing they try to throw at you. They give you the speeds. It's going 2 that way, then it's going 1 that way. That's a difference of 3, okay, meters per second in terms of velocity. You got 10 kilograms there, so 30 kilogram meters per second. All right. How about this one? You got a 2 kilogram object moving to the right with a speed of half a meter per second. Experiences the force shown. What are the object's speed and direction after this force ends?
After the force ends.
So after the interaction,
So that's
we
just
add
gonna
1 Newton second to whatever that is. So already 1 Newton second, so we get 2 Newton seconds divided by minus. It's just 1 Newton per second. Right, because it's positive. So yeah.
And let's see what we got here. Got 7 for D and 2 for E, and now we got nope. Now we got 9 for D. Now we got 10 for D. Got 11 for D. Got 10 for D. Got 12 for D. Got 13 for D. Oh my gosh, D's flying off the shelf. So talk to your neighbors about that one.
Yeah,
You could put
So it's asking for the
So we have, look at this graph. We want to find the impulse and change in momentum.
the change
F
has
of
to
1
be
half. So it's 2 and 1 half is 1 Newton second.
the change
So
of
you add 1 positive Newton second to it was already, right? What was already was,
Yeah, each one has 1.
no.
Yeah, so the one that makes
We actually know that it's going right, so I was like,
Yes.
when's the last time?
No, this one.
It says it's moving right, you're right.
No, because the initial momentum is 1.
yes. Initial is 1 and the change has to be 1. There's no point.
No, the change.
Is that wrong?
Yeah, I mean, it's also.
Because the area on this graph represents the change in moment, right? The impulse.
Yeah.
Okay, so then 1/2 times 2 is a change of 1, right? And because it's not negative, it can't be referenced, so why is it?
All right, now we got almost everybody going for D. And again, you've got a 2 kilogram object going to the right with a speed of half a meter per second, so that's an initial momentum of 1 kilogram meter per second. The impulse is the area bounded by that graph. It's 2 newtons by half a second, so that's 1 Newton second, for a total of 2 kilogram meters per second. Final momentum, 2 kilogram meters per second for a 2 kilogram object means the speed is 1 meter per second, and you're going towards the right. All right. So you had an initial moment. Again, man, goes to physics tests yet to come. You can figure out the initial momentum. You add the change in momentum to the initial momentum to get the final momentum. All right. 2 kilogram object moving to the right with a speed of half a meter per second. It experiences the force shown. What are the object's speeds and direction after the force ends?
Is it like a cover on your keyboard, or is it just like,
Oh, it's a cover.
oh, okay. I see the keyboard when there's like a bump in the middle, it's like,
So
I put B. Because before, it's the same force, but in the opposite direction.
All right, everybody and their mother is going for B here. Why B? We already wasted Ronan. Somebody else go. We're going to waste Sean now, too? Come on, hit the low-hanging fruit, people. All right, what do you got, Sean?
Well, the area of that is like negative 2 times 1 half equals negative 1, and that's equal to the change momentum. So if you add that to the initial momentum, which is already
Okay.
I know that if weighs something, that doesn't change. So the velocity has to be 0.
So there you go. Initial momentum is 1. Change in momentum is -1. You take the initial momentum, add the change of momentum to it to get the final momentum. I wish teaching was telling, because then you'd get that all right tomorrow, but hey, such is life. Force pushes a cart for 1 second starting from rest. To achieve the same speed with the force half as big, the force would need to push for got 13 in. Still waiting on one person. There we go. All right. And most people and their mothers are going for D here. Why D? EO?
Because you have to use a lot of force to get to that speed in 1 second. If you only use half as much force, you have to use double as much time, so you can get there more rapidly.
There you go. Got that balance thing happening. Smaller force, more time. All right. A light plastic cart and a heavy steel cart are both pushed with the same force for 1 second starting from rest. After the force is removed, the momentum of the light plastic cart is that of the heavy steel cart. What do you got? Pretty evenly split over A, B, and C here. So take a moment, chat with your neighbor, see if you can change their mind.
Yeah, what people are asking about, if it's momentum has to change the same, but they're different.
Go ahead and modify your vote as needed.
No, wait, that's incorrect. I was saying something wrong.
How's the plurality work? Somebody's in Gov. How does plurality work? Like a plurality of votes? Is that like when you have more than anybody else but not a majority?
Yeah.
Somebody? Anyways, all right.
That entire statement I said before.
So one of these has a plurality but not a majority. But most folks are going with either A and B. Okay, so take a moment and chat with your neighbor real quick. Man, you guys are sticking to your guns. All right. So we're pretty evenly split between A and B here. Okay. You're told that they have the same force for 1 second. Okay. So if they have the same force for the same time, that means they're going to have the what? What's the product of force and time?
Momentum or impulse.
Impulse.
Yeah.
Okay. Why did my face do that when he said momentum?
Because impulse is changing.
What did you correct yourself to?
Impulse is changing momentum.
Change in momentum. They have the same change in momentum here. Okay. Now they both start from rest, so then yes, they're going to have the same momentum. Okay. But yeah, the momenta are going to be equal, okay? Not greater than. What will be greater than? What?
The velocity of the smaller.
Yeah, the lighter cart will be going faster, but it will have the same momentum because it experiences the same force for the same amount of time. Okay, same force, same time, same impulse, same change in momentum.
It would have greater velocity.
All right. Oh, this is frozen. That doesn't work very well, does it? 2 1 kilogram stationary cue balls are struck by cue sticks. The cues exert the forces shown. Which ball has the greater final speed? Now, the thing that's missing on here for no good reason is the axis value here. This should say 10 newtons here on the second graph. See if that helps your answer.
So that's
Again, for those of you just joining us now, the vertical intercept for graph 2 should be 10 newtons. That has most people and their moms voting for C. Both balls have the same final speed. They have the same final speed. Why? Because? Grace, that could be construed as a hand in the air. Because there you go. Same areas in those rectangles, same areas, same change in momentum, same final speed because they got the same mass. This time they have the same mass. All right. You awake in the night to find that your living room is on fire. You have one chance to save yourself. It's to throw something that hits the back of the bedroom door and closes it, giving you a few seconds to escape out the window. You happen to have both a sticky ball of clay and a super bouncy super ball next to your bed. They're on different sides of the bed, of course. Both have the same size and same mass. You only have time to throw one. Which will it be? Your life depends on making the right choice. All right. Let's see where you land. I'm going to put a time constraint on it here. Pressure. This is your life.
okay. Well,
Bouncy ball is
bouncy ball,
because they have to like go back.
but
Yeah.
yeah, but the reason is just because
The change in-
it also has to change direction,
Yes.
which
So
causes
the
more
momentum
bigger.
that gives off onto the board. It doesn't matter if they're throwing.
Just
Get out. All right. How'd we do? All right. We got 13 physicists surviving this fire and 1 not. What's the key to this? Terwilliger. What's going to go on here?
Well, you want something that will, break the window, right?
We're not throwing it at a window. We're throwing it at the door.
It's,
Kyle was practicing this on your back the whole time. Kyle, you're the donkey that was throwing stuff. Why is the Super Bowl better here? Sad heart. Yes, Terwilliger.
well, you want something that will have the greatest change in momentum. So the clay ball will just stick, and it'll go from a positive to like just a positive velocity to just 0, while the super ball will go from a positive velocity to a negative velocity. That's why having a greater change in momentum.
There we go. Okay. Greater change in momentum with bouncing. A mosquito and a truck have a head-on collision. Which has a larger change in momentum? Still waiting on a couple friends here. All right, initially it was really split between A and C, but now it's not. So talk to your neighbor about why that is.
Well, the change in time is the same.
Yeah.
And the amount of force is the same because it's force pair.
Part of the is the same.
So change in
Yes.
It's always
force.
the same period of time.
Also math is different, but also change in velocity.
I mean, if you assume that there's.
All right, there's a little hint hiding in the corner. Hey, guy. So what's the deal here with this one? Braden, you got a hand in the air. What are you thinking?
So because we know that like they have the same about the same force hydron and their force pair. So and they also have the same, it's over the same amount of time. So they'll have the same change in momentum.
There you go. They'll have the same change in momentum. They will not have the same change in velocity. Their masses are very different, but they will have the same change in momentum. Hashtag forces come in pairs. All right, a 1 kilogram box is sliding along a frictionless surface. It collides with collides with and sticks to a 2 kilogram box. Afterwards, the speed of the two boxes is. Rona, we got this thing called Pear Deck. You can just type your answer and you can say it out loud. Emily's perfectly capable of looking over your shoulder from behind you. So. That would be my feedback to Pear Deck, is make it a little smaller because it's like easy to see on screens. And nobody struggled with this. Everybody's got B for this one. Because why? Pear Deck said so. Who's got me? Emma, what you got?
So forces are stiction.
Okay.
So therefore, you like in after rotation, you treat them like they're the same object. So the initial momentum of the first box is 3 kilograms per meters per second, and then the final object is 3 kilograms, but the momentum is the same because of conservation of momentum. So 3 kilograms per meters per second divided by 3 kilograms.
There you go.
We have a 5 to 10 lockdown through the end of school. So that means that you'll have